these are improper. Okay, so taking questions. We're going to take this is equal to. Let's go ahead and write what this is equal to. And then once we write what this is equal to, it's not a problem. This is equal to the limit as t tends to infinity. This is the definition of the integral from 0 to t of e to the minus x dx. This is equal to the limit as t tends to 0 from the right of the integral from t to 1 of 1 over the cube root of x dx, again by definition. This is equal to the limit as t tends to infinity of the integral from 2 to t of 1 over x, the natural log of x dx. And now let's go ahead and define what this symbol means. This is equal to, and now we need to find some place to separate these, okay? So we're going to say this is equal to something like this. The integral from minus infinity, we'll use 0 to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx. And so these things are defined, right? This is equal to the limit as s tends to minus infinity of the integral from s to 0 of 1 over 1 plus x squared dx plus the limit as t tends to infinity of the integral from 0 to t of 1 over 1 plus x squared dx. So we just do them separately. I'll take any questions about any of those definitions.
Will you scroll down just a bit for the parenthesis number 3?
Scroll up?
Oh, yeah, I'm sorry. Yeah. As far as making these improper, on each one of them, on the first one, it's infinity. Is that correct?
That's right. So 1, 3, and 4 are improper because infinity is not a number, and I'm putting a non-number in a place where a number has been.
And number 2 is because it's 0 on the bottom.
Right, because you're dividing by 0. Right, that's right. You're infinite at a point 0, and so it's not clear that that this is a finite number. We had remarked last time that if you have 1 over x to a power, then it's going to converge at a place where it's undefined if the power is less than 1. In this case, the power is 1/3, and therefore this one should work out. And so the question is going to be stated: determine if the following integrals converge or diverge. Converge or diverge. And already, those people who haven't been paying attention are just going to get thrown off by the terminology. All I'm asking is this a number? Is this a number? Is this a number? Is this a number? Or are these numbers infinite? Or are these things infinite, I should say? Okay. Questions about any of the definitions? We'll do the first one. We'll put it in black. So 1, the limit t tends to infinity of the integral from 0 to t of e to the minus x dx is equal to, by the fundamental theorem of calculus, is the limit as t tends to infinity. The antiderivative of e to the minus x is minus e to the minus x, evaluated from 0 to t. Notice what we're saying. We want to know the area under the curve of e to the minus x on the whole positive real line. Now, the argument goes like this. I'm pretty sure that this one converges, right? And the reason is because 1 over x squared converges, right? We proved that. And e to the minus x goes to infinity, goes to 0 way, way, way faster. And so now this becomes a question about, we're saying that if we want to calculate the area under a function on the whole real line, at least half the real line, then we're literally asking the question, does the function go down fast enough? right? And so when we look at the graph, of e to the minus x, the question becomes, does it go down fast enough? If it doesn't go down fast enough, then that means when we start adding up all this area under the curve, you start adding up too much. Imagine a curve like, I'll put that curve up in a second. Let's look at the exponential. So if I put in the exponential, plot the exponential at minus x, x equals 0 to 100. Now, all we're doing is adding up areas. Now, if we're adding up areas and we want to get a number, and we're going to say this in chapter 8, we're adding up areas and we want to get a number, then this stuff over here better add up to very, very little. Now, as we said before, e to the x, e to the negative x is 1 over e to the x. That's a fraction. The numerator is not 0. E to the negative x is never 0. But if we're trying to add up all the areas under this curve, and we want to get a finite number, and we're adding up forever, there better be practically nothing left. Okay? We cannot keep adding up more and more areas as we move to the right. And so the function, if we ask, well, is the area under the curve on an infinite interval, is it finite? Then we're really asking, does this function give you practically nothing as you move to the right? And that is true. Okay, so this is going to be a finite number. I'm asking you what it is. So finish this. So keep going. So plug in t0 and subtract, and then take the limit as t goes to infinity. You should get 1. The area is 1. And I guess we should do a more ridiculous example in just a second. This is equal to the limit as t tends to infinity, plug in t0 minus e to the minus t minus e to the, minus e to the minus 0. We were about to get negative 1, but we know the answer can't be negative 1, right? This is equal to the limit, and here is where people run into problems evaluating these limits. We need to know that the e to the negative t goes to what as t goes to infinity? As you move to the right, it goes to 0. We need to know that. Right, so that is 0. Right? And so this is equal to minus e to the minus t plus 1, and that is 0 plus 1, which is 1. Questions about that? So it's here that we need to recognize this step, right? That people lose a couple of points because they don't remember those things, about those properties about the exponential. Let's do another one. So when I plot, I'm going to plot something else. Let's plot 1 minus 1 over x squared. Let's do that. And I'm going to do that from 2 to infinity. So I'm going to make that 2 to 100. Let's do that. It's not happy with that. Oh, maybe I should call it x, right? X equals 2 to 100. Okay. And let me go ahead and do something like that. Fine. I'll do this one. Now I want to calculate the integral of this on the whole real line, on the whole positive x-axis, from 2 to infinity. Obviously infinite. Obviously infinite. Right? What's the theorem? What is the theorem? If I give you a function, that is that I'm going to evaluate on and an infinite interval, and I want to know whether it converges or diverges, what must be the case about the values of the function? Mostly. Here's the case where the values are getting closer and closer to 1, and clearly if I add up all this area from 2 to infinity, I'm going to get this massive number. What does the function have to do? If it converges.
Has to be a finite number.
No, but this goes to a finite number. This goes to 1. Right. Right. You have to be going down. You cannot be staying up. Right. Now, there's some pathological examples where there's some counterexamples. It doesn't have to go to 0, but most of the values have to go to 0. Okay. Most of the values have to go to 0. So all we're saying is that if you want to calculate finite area over an infinite interval, then most of the values have to disappear. That's all we're saying. That doesn't happen here, right? So here, this stays near 1 as x gets larger, and you're just adding up more and more and more area. Okay? I'll take questions about that. So again, questions about whether something converges or diverges on an infinite interval is a question about this better be vanishing pretty quickly, and the exponential vanishes very, very quickly. Okay? This one, 2. The limit as t tends to 0 from the right. The integral from t to 1 of 1 over the square root of, the third root of x dx is equal to the integral, that's just so bad, is equal to the limit, equal to the limit as t tends to 0 from the right of the integral from t to 1 of x to the negative 1/3. And then it's power rule time. Right? This is equal to, by the fundamental theorem of calculus, the limit as t tends to 0 from the right of add 1 to the power, divide by it, that looks like a 3/2 x to the 2/3, evaluated from t to 1. I'm taking the limit as t tends to 0 from the right because from the left, I'm not so interested in it. Again, it's the integral from 0 to 1. It's all the values. That means that the function is defined on the interval 0 to 1. So the only values I should be taking for the function should be values to the right of 0. Okay? And therefore, I'm taking the limit from the right. I'm going to go ahead and add 0 to 10 on this one. 10 being impossible. 0 being, please, please, please give me this one. 6. Oh, I'm sorry? You were going to say 6 as well?
Yeah. Why are you using t and 0 instead of t and 1? And why are they?
Oh, because the function there are no problems at 1. You plug in, the function is defined at 1, right? The problem is at 0, right? Okay. So the problem, we want to take the limit as t goes to the place where the function is having problems. Every function has problems at infinity, okay? And in this case, we would be dividing by 0 if you plug in 0 here. So there's no way we should be asking what happens when t tends to 0.
You change the exponential fraction to the 3 to the last line. 3 over 2.
I'm sorry, it is, thank you. It's 2/3, thank you.
Okay.
I'm trying to perform magic on you.
I thought you was teaching something new. We just having all kind of issues.
I know. Wait, let's just plug it in. I didn't move. I didn't do anything. I know, right? We'll start it up again. That's weird. All right, so let me just say to those people who are listening on the video that the screen has gone out for us. So we'll give it. Have we written down the other ones? Let's work on the other problems.
Okay. I'm confused as to the t and the 0 here,
Yeah.
and how it became a negative t.
Wherever there's an x, you put t. And
Oh,
wherever
this is
there's
a negative. Okay. All right. That's not confusing.
Okay.
All right. Then on this side, when we use 0, how come 0 didn't come first and then t?
Wherever.
So that's what you have written.
Oh, well, maybe I have it. I'm sorry. So. Oh, I'm sorry. You're plugging in 1 and t, right?
Right.
Yeah, that's a
why I
mistake.
was
Yeah.
asking.
You're plugging 1 and t, so that's a 1 and that's a t.
Okay.
Yeah.
Okay. Yeah. That's.
No, there's no zeros.
That's what I was
Yeah, you're
confused.
plugging 1 and t. You're plugging 1 and t.
That's what I'm wondering why you
That's where you say after you evaluate?
Yeah, plugging 1 and t and subtract.
Okay.
Yeah.
And so t is always 0?
T is going to 0.
It's always 0 right there. Okay.
Yeah, t is going to
So
0.
it's 1 minus 0. Or 3 halves.
You have to have a limit. I'm going to mark it wrong if you don't write
Oh,
it
yeah,
there.
yeah.
I'm going to be hard there.
No, that's fine. You should be.
How far do you carry out the limit?
You carry out the limit until you plug in the number.
Okay.
When you plug in the number, you don't need the limit anymore.
So that would be 1 plus 0.
Oh, well, then there shouldn't be a limit.
Yeah, if you put 0 there, there should be no limit.
You need to put the limit there, and then after put your number in, then
Okay, then it's.
And what's the answer here? 3 halves, right?
That will make it so much harder than it is.
Okay.
So fun.
Yes.
on the definition of
T to B. That's right, because so the integral that was given was the integral from 0 to 1 of this. So the integral from 0 to 1 of this. And the problem's at 0, so we need to put the limit as you go to 0. The problem's at 1. So you take the limit wherever there's a problem. So there's a problem at the integral, so you take the limit as t goes to the limit. So you put a t there back. Go ahead. Yes, they are. Yes. You plug in 1 and t. Yes. So that's backwards. Yes. Yes.
When you say, you're saying, I'm trying to build mathematical.
And I thought that there was, you said there's different ways. I was thinking that, but
Oh, so t tends to 0. T gets closer and closer to 0. T N D S. Tends.
Oh, I got you.
Sorry. Tends. I can't say the D part.
No, I got you.
Tends.
Well, I've never heard that before.
Okay, well that's right.
Despite of what's happening right now, you really do have the best handle on that machine than anyone. And here's the teacher I have. Everybody else is like pushing buttons. And they're like, what's happening right now?
Oh wait, what do you mean the best handle?
Like you actually know it. Like you're the one that needs to actually.
I know it works.
I know despite of what's happening right now.
Right, I know.
I
Right.
know it's your fault.
Oh no, it is not my fault.
Because it looks like it just decided to.
Yeah, it just stopped working.
But every
It
other
just stopped
class
working.
we have sound in their pictures, or like pictures and their sound.
Okay.
It never looks like.
Well, you know, technology. Campus of tomorrow. So am I supposed to say that on record? I guess not. All right. We'll give it one more try.
no, because you have to take the anti-direction of the one over. Like this.
And the problem is that the software is not even this old. It's not even like this is outdated stuff. The school's only 7 years old. So like, it's not like this is just old equipment. Right, it's actually pretty nice. Yeah, when it works.
We're stuck on that improper.
Of what?
1 over x ln x.
Whenever. Oh, good. That's good. That's why I gave it.
That's pretty good. No.
Okay, that's working. There's my hand. Very good. Okay, so this is working. That's this.
This is like a high-tech projection.
Yeah, no, we have some serious materials over here. It's like Star Trek shit over here. And this I believe. I mean, but you know, what?
It seems like it's not high-tech because it's just a projector that they spend more money on.
Right, now listen, I don't see any value in this. I mean, I don't. Yeah, it's not. No. Some people put their notes here and write their notes here. You know, like that's right. So you're just like, look at my hand. Right? Look at my hand. I'm reaching out for you. Right. Okay. Now, I guess there's something up with the connector. So that's good because there's nothing on that screen. And now, there's nothing on that screen. But now let me plug this in. There we go. All right. Well, let me. All right. Will it go out again?
Let's hope not.
You're good? Okay. All right. So now we're faced with the antiderivative of 1. Did I make that the second one? Or the third one? I'll take any questions about the first two. So tell me what makes this a 6. What's the hard part here? Okay. Okay, that's good. Thank you. Other reasons why this is okay. So again, when you're going to infinity, well, I have to give the mathematical reason and then the off-the-record reason. So the off-the-record reason, people like instant gratification. Let me give you that one. Yeah. And if you're going to the place where you're undefined, that's where you need to take the limit.
But how would you even? I feel like I wouldn't look at number 2 and be like, oh, that's clearly going to have a problem there. Like, how do you?
Oh, because now we always have problems when we divide. We always have problems when we divide.
I mean, because 0 would make them undefined.
Right.
Okay, cool. Got it.
Now, okay. Well, let me also give the mathematical reason. She's now tuned me out. But okay, so that's a quick and dirty way of saying again that here the limit is x tends to 0 from the right of this is infinite. And again, in order to invoke the fundamental theorem of calculus, we cannot be talking about functions that become infinite on the interval, right? When we were talking about finding the area under a curve, at no moment was the function ever infinite. It was nice and continuous on the closed interval a to b, and therefore it was finite, right? So if it becomes infinite at 0, then clearly we need to make it finite, close to 0, and then let that place go to 0. That's the game plan. Say it again?
What's the answer to that?
Oh, I think it was just 1, right?
No, it's 3 halves.
Oh, 3 halves, I'm sorry. And so this is equal to erasing this madness. Plug in 1 and t and subtract. 1 t is equal to the limit as t tends to 0 from the right of 3 halves minus 3 halves t to the 2/3. And now we plug in 0 for t, and that is 3 halves. Questions about that? I gotta learn how to use this space over here. This always happens. I think this happened on the last page. And this is only the first page.
When you write without lines, it goes correctly. Yours is actually straight. I go like right
Yeah, well, I've been doing this a while. It's okay. All right, number 3. The integral 1 over x, the natural log of x, dx. Right? The question, of course, is 1 over x times the natural log of x, does that go to 0 fast enough? Does that go to 0 fast enough?
See, I thought that would turn into 1.
What turns to 1?
X times 1 over x.
No, it doesn't. It does not turn to 1. X times the natural log of x.
I knew it wouldn't be that easy.
X equals 2 to 100. I'm picking 100 arbitrarily, okay? The question is, area under this curve, finite or not?
Finite.
You think so?
Yeah, it's getting smaller, right? So
And it is getting smaller. But so did 1 over x. 1 over x got smaller too.
Can I ask a question that's
Please.
like irrelevant?
Relevant or irrelevant?
It's relevant but irrelevant.
Relevant to this?
Okay, never mind.
Okay. Okay. No, yeah, you can ask it later. I'm just trying to figure out how it's relevant and irrelevant. So.
It's the same stuff, Joe. Yeah.
Oh no, you can ask. Yeah. Once we're done with this, once we switch to another section, you can ask me.
Okay.
Oh yeah, that's not a problem. Okay. So as x tends to infinity, will this go down fast enough? I'm worried at 100 already.
yeah.
That I can see it. Right. Now, e to the minus x, you couldn't even see any space under the graph, right? E to the minus 100 is 0 to so many decimal places. So the fact that at 100 there's still this space here, I'm worried. I'm worried that it's too much. All right. Now I could be worried. I could be wrong about that. But let's see what happens. In order to do this, of course, as someone has already remarked, we need the antiderivative of this. We're going from 2 to infinity. This is equal to the limit as t tends to infinity of the integral from 2 to t of 1 over x, the natural log of x dx. This is equal to the limit as t tends to infinity of, how are we doing this antiderivative? We try to hide it from you. Writing it this way is pretty obvious. We should do what? What's the integration method? What's the integration? How do we find the antiderivative of this?
Is it let you
Equal
ln of x?
the natural log of x. That's right, because 1 over x dx is here. Right, so we'll let u equal. So we'll step aside and we'll say, well, 1 over the natural log of x times 1 over x dx. We need that antiderivative. We'll let u equal the natural log of x. And that is a pitiful natural log of x over here. The natural log of x. We'll let u equal the natural log of x. Du is 1 over x dx. I'm worried. I don't think that's going to work. This is equal to the antiderivative of 1 over u du, and the antiderivative of that is the natural log of u plus a constant. But then u was the natural log of x. And so this is the natural log of the natural log of x plus a constant. And this constant we're not going to write when we actually plug this back in. This is a remark. So now that we have the antiderivative, we'll plug in t and 2 and subtract, and then take the limit as t tends to infinity. So this is equal to, by the fundamental theorem of calculus, the limit as t tends to infinity of the natural log of x evaluated from 2 to t. This is equal to the limit as t tends to infinity of the natural log of t minus the natural log of 2. And that is infinite. It's too much.
Are you missing one natural log from the top? When you substituted u, you still had a 1 time.
Maybe I'm wrong.
1 over x at the top. Would
Wait.
that come back in?
Wait, where?
At the very top.
At the very top.
Before you substitute. No, not the very top. Stop right there. The limit, you have 1 over natural log of x times.
Yeah.
1 over x.
Right, which is here.
Oh, right. Well, okay, it's substituted. Sorry.
Yeah.
Okay.
Questions about that? Again, we need to know something about the natural log, that the natural log tends to infinity as t tends to infinity. And therefore the natural log of the natural log also. That's right. That tends to infinity. The whole thing tends to infinity. And who cares what that little number is?
Okay.
No? Questions about that?
Infinity, you said you don't care about the, I didn't hear what you said.
Right, so thank you for your question. So now, here's where the problem comes. We ask ourselves that, where does this go as t tends to infinity? And so we need to know that the natural log tends to infinity as t tends to infinity. So the natural log of that will also tend to infinity. So this is infinite, and this is finite. The whole thing's infinite.
So you would say this diverges?
Absolutely. This diverges. All we're saying is that, again, too much area. You add up all of this area, it gets arbitrarily large. Yes?
How many of these do you think we're going to have?
No more than 3. But how many would you like?
1.
1. And which one would it? But I have to give you one on an infinite interval and one on a finite interval. That's why I was thinking 2. Right. So I mean, there's yeah. But I'm missing. What exactly is the problem? What exactly? How are these different from the other integrals? This one is just like a little sick, and I mean because you have to see the observation. But this one here, you just find the antiderivative and take the limit. That's what I'm asking you to do. But no, I appreciate you being honest. If it's, I'm just missing exactly what the. I don't think these are that much different from like the other integrals we've been doing. But again, I could be wrong. I mean, I haven't been a student in a long time. So I know I'm the first to admit that I'm disconnected from you. I feel like you're going to make me go back. You okay? Yeah. But being a student today is much different from being a student back when I was a student. And that wasn't that long ago. I mean, 15 years ago. But things are different. So when I say something's easy, I am unqualified. I'm unqualified to say that something's easy or difficult. Okay? So when I do that, it's just bullshit. You should call bullshit on me. I mean, it's easy to me, right? But I'm not the student. Okay? All right. We got one left, right?
Yeah.
This one. We're going to go from minus infinity to infinity, 1 over 1 plus x squared dx. Now that's the whole real line. That's the whole thing. is it possible x equals minus 100 to 100? Ha! Plot. All right. Finite or infinite?
Infinite, because you have all that
That
space,
100
just like you did on the other one.
So yeah, no, but you know this one may work out. So that's what's nice. What's nice is that I can hand wave with the other one, right? So, yeah, so I think it's pi.
Well, I can tell you the derivative is.
You think it's infinite?
tangent inverse.
Fine infinite. So if you go with it,
Say it again. Oh, find infinite. Find infinite. Find infinite. I would love to hear that definition. The definition of find infinite.
it goes both ways.
Right. That's right.
Some think that these are finite or infinite.
Exactly.
I think it's 3.14159, something like that. Okay.
How do you just know that way?
Finite is, yeah, maybe.
Right.
What'd you say? PhD, that's right. Let's go ahead and see why this is. Okay, so this is equal to. Now we have written this as the limit as s tends to minus infinity of the integral from s to 0, and again I'm choosing 0, of 1 over 1 plus x squared dx plus the integral from, the limit. I'm going to split them. I'm not going to go to infinity and minus infinity at the same time. All right. So there's a problem at infinity. There's a problem at minus infinity. We'll separate the problems. Now I could have picked 5. It doesn't matter. I could have picked the integral from s to 5 plus the integral from 5 to t. I could have done that. 0 is just a nice number.
Yes, tangent inverse. So tangent inverse.
Questions about this?
So I can put a remark in my notes. Why exactly is the S because you have infinity and negative infinity?
That's right.
Okay.
That's right. So I have to do two things. There's a problem here, a problem here. All right. We need the antiderivative. What's the antiderivative of 1 over 1 plus x squared?
Tangent inverse.
It's the inverse tangent. That's right. As the limit is s tends to minus infinity, and by the fundamental theorem of calculus, this is the inverse tangent of x evaluated from s to 0 plus the limit as t tends to infinity of the inverse tangent of x evaluated from 0 to t. We'll plug in 0 in s and subtract. Here, this is equal to the inverse tangent of 0. Whew. This is equal to the limit as s tends to minus infinity of the inverse tangent of 0 minus the inverse tangent of s. Now, and you can already see it's very difficult to keep writing the limit. I keep forgetting to write it, so I'm not going to be too harsh on you, but write it. I always remember to put it there. Right? There's just something wrong with the universe when I don't put it, and I don't write it. Plus the limit as t tends to infinity of the inverse tangent of t minus the inverse tangent of 0. The angle whose tangent is 0 the angle whose tangent is equal to 0. What is that? That is 0. That's right. So this is 0. Because the tangent of 0 is equal to 0. That's what the inverse tangent means. So here's the remark. So the remark is this. The inverse tangent of 0 is equal to 0. And that's because that's true if and only if the tangent of 0 is 0. That's why that works. Now I need the inverse tangent of infinity. So I'm asking, what angle makes the tangent infinite? There's an angle. There's an angle where the tangent is infinite. You need to plot it. What is tangent by definition? That's right. What angle is that? No, it's not at the top.
2 pi, wait.
Pi over 2. 90 degrees. Exactly. Very nice. 90 degrees, pi over 2. So tangent is infinite at pi over 2. Where is it negative infinity? Say it again? No, that's not in the domain. It's negative pi over 2. That's right. That's really good. Okay. So this is equal to zero. This is from the remark. We're going to apply the limit. That's minus negative pi over 2 plus pi over 2 minus 0. What?
You make it funny because I write like 12 different colors.
Yeah, hey, it works with some people, right? It works.
I find that easier is
Oh yeah, no, because I think I do that because it does keep people.
And it makes like, it separates like you go off to the side and say something.
Right. Oh, definitely for a remark. If it's not if it's not directly in the problem, I'm going to change the color.
I think we just have fun changing.
Oh, that's true too. That's obviously true. Yeah. It's like coloring. All right. So again, I don't envision giving one like this, but I just wanted to make mention of it. I'm going to take questions about improper intervals. I'm going to ask 2 of them, one on an infinite interval, another on a finite interval. Are we good? I've given homework. Yeah, I've given homework, yeah. All right. 7-7. This is 7-7. Please. Where? Oh, wait.
Because I have to plug in values to see how consistent.
Oh, no. That's when you have to ask me. Ask me during the test. Ask me during the test, and you got to flip a coin as to whether I'm going to tell you. But usually I do tell you. People usually people will say, well, what's the limit as t goes to infinity of the natural law of t? And then I'll say, that's infinity. So, okay.
So then you'll be our calculator for the test.
I'll be your calculator for the test. That's a good way of putting it. Okay.
You can just avoid the Trinity thing.
Right. Right. All right. We're ready for the last section before the test. But now you had a question that was semi-relevant.
Oh my God. Oh yeah. What's the major difference between calculating linear algebra?
Oh, Calc 3. Okay, so here's the. So Calc. What'd you say?
Like somebody like pull out your iPad and do like.
Yeah, I could do that, but then it wouldn't be recorded here. That's the problem. I mean, I would do everything on the iPad if it could record. The presentation would be much more dynamic. But it would be. It would just blow this away. But so in Calc 3, we're talking about, I think it's just this simple, plot. We're talking about 3 dimensions, right? Of
Yeah.
z equals, let's do something like this, x squared x squared plus y squared. And let's say x equals, let's say, minus 1 to 1. And then I think it's y equals minus 1 to 1. It's been so long since I've done this. Is it that simple? Right. So now, so this is just the bowl, right? So, but here I'm claiming this is a function, right? So I'm claiming this is a function. If that's true, then I need a domain and a range. So what's the domain here? Right, so there's the box. What's the domain? I'm going to give you an x and a y, and then you give me a z. Okay, so you got to give me, so the point 1, 4 goes to what number? 1, 4 goes to 1 squared plus 4 squared, 17. So if I went down here to the point 1, 4, but this is not in my domain here, so I have to say 1 half, 1 half. So 1 half, let's say 1 half, 1/3. 1 half, 1/3 goes to 1 half squared plus 1/3 squared. That's 1/4 plus 1/9. Okay. So when you go in this box down here, at the bottom, 1 half, and then 1/3, it goes up to that value, z-wise. Right. So this is actually more realistic because the functions that we have, well, we live in 3 dimensions. We live in 3 dimensions. Right. So calculus is about asking, you know, the calculus in 3 dimensions, which is what Calc 3 is about asking all the calculus questions about 3-dimensional objects. Right. Where's the minimum value here? It's here, right? That's the minimum value. It should not be so surprising that that is the place where you're flat. Okay. So that the notion of derivative should not be bounded to only 2 dimensions. So in Calc 3, there's a notion of derivative. What is the area, now in this case, what's the volume under this graph? Right. All right, so we'll need to take 2 integrals, okay, to do that. Okay, we'll need to take an integral in the x direction, and then we'll need to take an integral in the y direction, right, to figure out what the volume is under this curve, right? So Calc 3 is just asking all of the calculus questions about real functions, right? Functions that depend on more than one variable. Now, linear algebra has to do with a lot to do with linear things. And so what does that mean? That means that you're going to have something like, you want to solve 2x plus 5y equals 12, and 6x plus 10y equals 15, and you want to solve for x and y. Okay. You can see that they're related because here I have 2 variables, x and y. Right? I have 2 variables, x and y, and nothing stops me from having x plus y plus z equals 30, and then 2x plus, and so forth. Okay, so having 3 equations and 3 unknowns. And so linear algebra has, and they intersect, but they are not the same subject. Right? So linear algebra helps out a lot with Calc 3, so much so, of course, that Georgia Tech requires it. Right? But they're different subjects that help each other out. Is that okay? Oh, is that why you were asking? Okay. Now, why it has to do with Calc 2 is not clear, but they spend a lot of time in their Calc 2 doing linear algebra, and that just doesn't make any sense. Well, it makes sense because all their Calc 1 is basically Calc 1 and Calc 2 here. Right. Right, exactly. So,
how
yeah.
is the Calc 3 only 3 credit hours in this class before?
That's a great question, too.
Because it ruined
Yeah.
the whole next semester because I was going to take physics.
Wait, no, is that true? I don't know if that's true. I don't know. I think Calc 3 might be 4 credits.
I thought it was 4 credit hours.
No, I think it's 4. I think it's 4. I think all the calculuses are 4.
It should be.
But is that okay? Does that answer your question?
Yes.
Okay. You're welcome.
3.
Is it 3? Okay. Well, wow.
Yeah.
All right. The final section, 7.8. Differential equations. My thesis ages ago, actually not ages ago, in 2005, was on partial differential equations. All right, so here's a typical problem. So, by the way, differential equations are the most applicable use of calculus in the sciences. Okay? And the reason is because things change. Here's an example. I'm going to let P of T, I'm going to talk about an environment. So I'm going to talk about an environment with just, and the environment's ideal, and we're going to put a bunch of rabbits in this environment. Okay. So here's one rabbit, here's another one. They're of opposite sex, okay? A number of them, okay? And we're just going to let rabbits be rabbits. We're going to let rabbits be rabbits. And now we're going to let P of T be the population. Okay? So we're going to let P of T be the population. To the population of rabbits. At time T. What's going to happen to P of T? It's going to increase, right? It's going to increase. How? Exponentially. That's what we want to prove. That's exactly right. That's exactly right. Now, we talk about that in pre-calc, right? Hopefully. But they just give you the formula in pre-calc. They give you the formula. Here we're going to derive it. All right? We're going to derive it. We should be like, oh, awesome. That's what the response should be. Right? But we're going to talk about what. But see, again, in pre-calc, right? If we're good students in pre-calc, when they say this is the formula for population, and you say, why? Why is that? That's such a great point. That's such a great point. And so I put the onus on you. I'm saying that you're not being the best student, but then when your professor's just like putting the smack down on you for doing that, right? Then that's also not your fault. That's a very good point. That's a very good point. Okay, but we should be asking nonetheless. Why is it that the exponential represents growth and decay? And it's because of this following assumption, that the way that we model, rabbits are going to be rabbits, and in the ideal situation, that means tons and tons, right? And now we come up with this notion that it's just going to be exponential increase and decrease. Why are we using the term exponential? And here's the reason, because the assumption is that the rate at which the population increases is directly proportional to the population at the time. And we've already been saying that, right? We're saying that the more rabbits you have, the more rabbits you're going to get. That's literally what this statement says. Right? That you're going to get more rabbits. The rate of increase of rabbits is directly proportional to how many rabbits there are. The more rabbits you have, the more you're going to get. All right, so let's go ahead and make that clear. All right, just in words. Do I have the arrow? Here's the arrow. So the rate, the increase in rabbits, so we'll put it in rate. Increase in rabbits. Oh, I'm sorry. Yeah, right.
Everybody's worried about stomach.
And then this is the rabbits at time T. So rabbits. So the statement is that the more rabbits, now, the more going the way. That's all that statement says.
Is that random? lambda or is that the?
Lambda, no.
Alright, get the, is that one because, I don't know.
That might be, no. If there's a Greek letter, I'm going to use lambda first.
Is that just one as a number?
That's right.
Okay.
So when I say that they're proportional, I haven't said exactly. So how proportional are they depends on the animal, right? So maybe lambda is going to be big for rabbits, but for turtles it may be smaller, right? What function satisfies this? That when you take the derivative of it, it's just a multiple of itself. I need a function, so when you take the derivative of it, e to the x, for sure. For sure. Right? So what's the solution to this? So let's suppose for a moment that it was 1. So for example, if lambda is 1, then I'm looking for a function whose derivative is itself. Seems like t of t is just what? A function whose derivative is itself. E to the t.
Well, if that's just one, you only have one rabbit, right? Or
I'm sorry, if lambda's 1?
Yeah. Are you saying that you only have one rabbit?
No.
Oh.
Lambda, let's look at the units of lambda.
Okay.
Lambda, no, I'm not saying you have 1 rabbit. I'm just saying that
Oh, the proportion. Okay.
right, the proportion is 1, right? Okay. Now, nothing stops me, of course, from putting something in front of this. Okay, so it could be 5 e to the t, 10 e to the t. So it's a constant times e to the t.
Are they constants according to species?
Of course, yeah, the constant depends on the species. Okay. But that's why it's exponential. That's why it's exponential. Okay. Questions about that? Now, what's wrong with this model? We never live in ideal environments.
Yeah.
Right?
You're gonna run out of
So,
room.
yeah, you're going to run out of space, resources, all of those things, right? Okay, so, of course, there are other models, okay? But this is one of the simplest ones, okay? So, when we had a lambda here, what if it's a 2? Right, so if lambda is equal to 2, then what is it? It's c e to the 2t for sure. Okay? So in general, it's e to the lambda t. It's e to the lambda t. It solves that differential equation. This is our first example of a differential equation. This is a differential equation. We're experts in algebraic equations. X plus 5 is 30. That means that x has to be 25, right?
That was back when stuff made sense.
That's right. X plus 25 equals 30. Let's do that one. That implies that x equals 5, right? And so 5 is a solution of this because when I plug in 5 and do the algebra, it solves it, right? But now if I say p prime is equal to 3 times p, right? This is another type of equation. This is algebraic because the operations here are algebraic. This is a differential equation because the operation here is differentiation, right? And so now I was looking for a number that solves this. Here we're looking for a what? A function p that solves this. Here's the exercise. Show that p of t equal to 10 e to the 3t solves p prime equal to 3p. Okay, and we'll go ahead and make that the last question of the exam. At least part A of it. Part A, last question of the exam, this. So that this solves this differential equation. And all we're saying is that if we took the derivative of this and then multiplied 3 times this, what's the relationship between the two? They're equal. I want you to show that they're equal. That the derivative of this and 3 times this are the same thing. That's all this is saying. That if this solves this, that means if I took the derivative of this, it's the same thing as 3 times this. Right? That's what made 5 solve x plus 25. When you plug in 5 for x, add it to 25, you get 30. If I took the derivative of p, I should get 3 times p. That's what I want you to show me. So what's the derivative of p? Let's do it. So the derivative of p prime of t is equal to what? 10e to the 3t times what? For sure, by the chain rule. That's 30e to the 3t. If we just look at what 3 times p of t is, well, that's 3 times 10e to the 3t. And what is that? That's 30e to the 3t. So that's a solution. So p prime is 3p. T squared is not a solution to this differential equation, right? The derivative of t squared is 2t, but 2t is certainly not 3 times t squared. They're not the same function, right? Right? T to the 7th is not a solution to this, right? The derivative of t to the 7th is 7t to the 6th, and that is certainly not 3t to the 7th for every t. Okay? That's what we mean by it solves that. Okay? Questions about that? About this here. Let's do another one. I'm going to use y as the function. How about this one? Y prime try y double prime. Y double prime plus y is equal to 0. There's a differential equation using the second derivative. Show that y equal to the sine of x solves. I'm going to call this star. Solves star. All I'm asking you to do is find what y double prime is, find what y is, and add, and they should cancel. Yes? Yeah. We got it. Y double prime, we need it. Well, first of all, we need y prime. Y prime is equal to cosine x. And that implies y double prime is negative sine. Well, y with sine, you add them, nothing. So it's a solution. Questions about that? Yeah, so I'm going to give you what I think the solution is. On the test, I might say, is the following function a solution? And it might be or it might not be, right? So that means you need to, so is e to the x a solution to this? Right, you take the derivative of e to the x, you get e to the x. Take another derivative, it's e to the x. You add that to e to the x, so you get 0? No. So e to the x is not a solution. Okay? Questions on that? Is e to the negative x a solution? And you can test it out. Test it out. Right? So I don't think so, because it returns back to itself. Right? I think e to the negative x solves y double prime minus y is equal to 0. Right? All right. Here's an application. So I'm going to come in and oh, we have water here. How cold is it in here? What's the temperature in here? Freezing. So what would you say? 60, okay, 69 degrees. And so here, the temperature of the water, what do you think it was? Colder or hotter than 69 degrees? Colder. All right, so that started off at what? 22 degrees. All right, so we come in, and now we want to know the temperature some later time. What's the temperature at some later time? So we're going to let T, capital T, little t, be the temperature of the water at time t. Let's go ahead and say it's 70 degrees. Nice round number. 70 degrees in the room. The temperature of the water starts off at 22 degrees. Okay. This is what we do as mathematicians. This is what we do as scientists when we want to use mathematics. I want to come up with a model that is going to give me the temperature at a later time. Right? She brings it in here at 10 o'clock. It's 22 degrees at 10 o'clock. I want to know how cold it's going to be at noon when the class ends. I'm going to be nice. It's 11:45. At 11:45 when the class ends. Right? 105 minutes later, when T is 105. Okay? What should this look like? That's exactly what it should look like. That's right. What should it look like? How? Right? So someone says, clearly it goes up, right? But this is what all of Calc 1 is about, right? Calc 1 is about, well, we know it has to go up and approach 70 degrees. By whose law? Whose law? Begins with he's kind of important in this context. Newton's law of cooling, right? Newton's law of cooling, and in this case, Newton's law of warming says that if you put an object of 22 degrees in this room that's 70 degrees and you leave it alone, then over time the temperature has to approach 70 degrees. Okay. So we know it's going to approach, but all of Calc 1 was distinguishing whether it looks like this or whether it looks like this. Right? Or maybe it looks like some wicked thing, right? So maybe there's something like this, right? Which one is it? And so Calc 1 was about how concavity, right? This is concave down, that's concave up, that's a little bit of both, right? So all Calc 1 was about that, right? But which one is it? Which one, for our model, if we want a model for this, which one should it be?
I think it's going to increase quickly and then slow down.
Right, so you're saying something like, you want something like this? It looks like it's up and then turns down. It looks like there's an inflection point. Right? Or it could be something like this. That's what you were saying earlier. Okay. Well, let's see which one is going to be. Here's Newton's law of cooling. Newton's law of cooling. Newton's law of cooling says something about the temperature, the way the temperature changes. The way the temperature changes should be should be proportional to what? Say it again. No.
The difference in the room temp and water temp.
Say it again.
The difference in the room temp and water temp.
That's correct. That's absolutely right. The temperature in the room minus the temperature at the time. That's really good. Well, you like this line better? Okay. Does that make sense? Yeah. Right. So that so that you know where you are. The rate at which the temperature is changing depends upon how close you are to 70 degrees. The closer you are to 70 degrees, should you be changing that much? No, you shouldn't. That's why it looks flat near 70 degrees. The farther you're away from 70 degrees, the more you should be increasing. That screams this one. Looks like it's this one. Why would it be flat to start? It's at 22 degrees, right? And it's trying to get to 70. It seems like it needs to run there. Right?
So it'll increase quickly at the beginning.
Okay,
Slow down.
very good. Right? Anyone thinks it should be this one? I've just biased you. But we'll see. It could be that, and then we'll have to explain why. Right? So I guess I want to do this in a nice way. Y prime equals k times 70 minus y. Right, so we'll drop the t for a moment. I'm going to solve that. What do you think the k depends on? The fact that it's what? What does k depend on? I said it's proportional. What is that constant? What does that constant have to do with? Water. It has to do with water. It's a statement about water. That constant would be different if it were Coke, okay, or if it were apple juice, right? Maybe. Right? We want to solve this. Y prime equals k times 70 minus t, right? So I'm going to use Leibniz notation. dy dt is equal to k times 70 minus y. Okay? And so what we're going to do is separate the variables. There are two variables here. We're going to separate the variables. So we're going to get y and t on opposite sides. And so for this example, I'm going to go ahead and let k be 2. Okay, so I'm going to let k be 2 because I don't want it to be too abstract. And so now we have dy dt is equal to two times 70 minus y. Okay. Questions about that? Is that okay? All right, now what do I mean by separate? Well, I'm going to remark that dy over 70 minus y is equal to 2 times dt. That's what I mean by separate. I'm going to cross multiply. So I'm going to bring all the y's over here, and I'm going to bring this dt over here. So that's using the notation. So here we've separated. And here's where we have to be very careful about putting absolute values on the natural log. All right, and now we're going to integrate both sides. Integrate both sides. Let's remember what we're doing. We're trying to find what y is. We're trying to find what the temperature is at any time. Once we find what y is, then it's going to be a function of t, and that will be the temperature at any time t. That's a remarkable thing. right? Let me just say that the typical example is really more morbid. You walk into a room and someone is dead, okay? And you want to know how long they've been dead, right? I know. You want to know how long they've been dead. It's Newton's law of cooling, right? Right? You know, you're trying to figure out when is their time of death. How long ago did they die? Right? You know that the temperature, my biology people, what's the temperature for 98.6 degrees? 98.6 degrees, right? 6, right? That's what it's supposed to be, right? And now you go and check them and it's 32 degrees, right? So, how long have they been dead? Right, how long have they been dead, right? Yeah, right, that's right.
You hear about crazy people that do that?
Who do?
Like women, like husbands will die, and they're still gonna get Social Security, so they'll like put his body in freezer.
Oh, well, yeah.
Isn't that crazy?
That is our story of the day. So, thank you. We need to know how to integrate this. The antiderivative of 1 over 70 minus y, gy, what is that? How would we do that? That 70 minus y, and du is minus dy. And so, say it again? Uh-oh. Yes, I am too, apparently.
Oh, yeah.
The antiderivative of 1 over 70 minus y, dy, u is equal to 70 minus y, du is minus dy, and so this becomes minus the integral of 1 over u du, which is minus the natural log of the absolute value of u plus a constant. So we separated the variables, got each one on one side, and then we integrated both sides. That's how we're going to find what y is. And one would expect that if I give you a differential equation, if I give you an equation that involves the derivative of a function y and I'm looking for it, in order to get what the function is, obviously I'm going to have to take the antiderivative at some point, right, in order to unravel the function. All right, so that's good. This is minus the natural log of the absolute value of 70 minus y, right, plus a constant. Okay? So we had the integral of 1 over 70 minus y dy is equal to the integral of 2 dt. Right? That was here. Right? That was down here. Right? Okay. And so we have the left-hand side, minus the natural log of 70 minus y, and I'm going to put the constant on the right-hand side. It's equal to the antiderivative of 2t plus a constant. There's a constant on both sides. I'm going to put the constant on the right-hand side. Questions about that? Sure, it can be.
Okay.
Yeah, I mean, C is arbitrary, so it can be whatever constant you want. You can make it positive, negative. I will put that minus sign on that side. The natural log of 70 minus y is equal to minus 2t plus a constant. You can write minus a constant if you like. But now, you only go now to solve for y. This becomes pre-calculus now. What is this function y? And then we'll plot it. Okay. What do I do to both sides? How do I get rid of the natural log? Whew. Right, you take you raise both sides, you raise the exponential of both sides, right? So that means this, e to the minus 2t plus a constant. Right, so e to both sides. So 70 minus y is equal to, and then we can do something with that, but I'll stop. So again, there's a differential equation You got all the y's on one side and all the t's on the other side and integrated both sides, and now we have to solve for y. It sounds like I need to talk about some steps at some point. I'm waiting for your decree.
Well, you were talking about steps.
Yeah, I was talking about, but I haven't written them down. I want to put them down. I want to write them down. We good here? We should remark that this is e to the minus 2t times e to c, e to the constant. Right? So that this is just a constant. That's just another constant. And we'll write it as a e to the minus 2t. Okay. Now, here's an example where the math has no idea about the context of the problem. That's what we have. I need to now take absolute values. I'm going to drop the absolute values. How do I pay for that over here? What do I have to put in front of here? Which one? Or we write that as plus or minus. It's one or the other, right? If I'm going to drop the absolute value sign, it's plus or minus. And now we just have to figure out which one it is. Okay. Solving for y. Y is equal to 70 plus or minus ae to the minus 2t. I put the 70 over there. That 70 is negative, and then I put the minus sign over there. That makes that minus 70 positive. But that plus or minus is still plus or minus. It's one or the other. Now the context of the problem, is it plus or is it minus? What is it that we want to see about the function? What do we want to see about the function? It should be what? It should be increasing. Yeah. Okay. So which one does that mean it is? So let's look at the picture. Right. It should be negative. That's right. That's really good. Both of you. Both of you two.
Oh.
Both of you two. For that one question at least. So y of t is equal to 70 minus ae to the minus t. And by the way, 2t. By the way, we could have figured this out, and let's figure it out the real way. Right? So we have this, right? So what do we know about the beginning? I need this constant. What is capital A? How do we find it? How do we find the constant?
You set t equal to 0.
Do we know what happens at 0? Do we know how much it was at time 0?
Yes.
What was it? It was 22 degrees. Okay, so we use that to find what the constant is. Right? So we'll recall that y of 0 is 22. By the way, with this differential equation and the initial condition, how many solutions are there? One. One and only one. On fire. You're on fire today. So 22 is equal to y of 0, which is equal to 70 plus or minus ae to the minus 2t. And so minus, I'm sorry, this needs to be a 0, I apologize. 2 times 0. So 22 equals 70 plus or minus a. But so what is it? So minus 48 equals plus or minus A. Now at the beginning, the temperature has to be what? 22, right? And so that means A has to be negative 48. Let's test it out. The claim is that the function is y of t equals 70 minus 48 e to the minus 2t. When you plug in 0, do you get 22 degrees? When you plug in 0, 48, 70 minus 48 is 22. Let's plot that. Plot 70 minus 48 times the exponential at minus 2t. And then t equals 0. Let's say for the first 5 minutes. The first 5 minutes, what happens? It does go fast. Right? And why does it go fast? Because I picked a big number for what letter? For K. For K. And when you do these problems, you'll see that K is usually some decimal. It's like 0.001 or something like this, right? If we had made K 0.001, then we would get something different. Like we would get a slower process, right? So we made this 0.002, right? So 0.002, we get something like that. And it's going to take a while, right? It's going to take a while to get there, right? So we need this on the first, let's say, 100 minutes, right? So it's hard to see there. So e to the, so we need to make it 1,000 or something like this, right? So there we go. So eventually it goes up like that. And it's the model is exactly how we pictured it, right? It goes up immediately, right? What's the temperature after 100 minutes in this case? You just plug in 100. What's the temperature after 50 minutes? You plug in 50. That settles it. Okay, that's Newton's law of cooling. I'll take questions on that.
What is K? What exactly is K?
Oh, K is a number that represents the rate for the type of substance you're talking about. So for water, it's one thing. For a dead body, it's something else. Right? So that number changes. Questions about that? Questions about this procedure?
You write down the steps.
Say it again. Oh, steps. Yes, let's do some steps. See, that's why I need to be reminded. On the test, I'm going to ask a question about Newton's law of cooling. Say it again. Oh, really? You like that? Wow. I'm going to put a turkey in an oven. The turkey's going to be frozen, right? And I'm going to have to thaw it, and then I'm going to need to know the temperature at some later time. I'll take questions about what I'm asking on the test. Do we see it's the same question? Right. What do I have to tell you in order to make this problem fair? I need to tell you what I've set. So I'm going to set the temperature of the oven at 450 degrees, right? And what else do I need to tell you? The temperature of the turkey, and the game's over. All right? So I'm going to give you some problems for the 7.8, and then you just do a bunch of them, okay? Now, I also might talk about population, bacteria population, and I might give you the rate at which the bacteria changes and all that other stuff. But don't be intimidated by the question I ask. Again, the brilliance of the subject is that I can answer a question using this method for the dead body, for the turkey, doesn't matter how you phrase the question, right? So differential equations are in biology, they're in chemistry, chemical reactions, they're in all over the place, okay? All right. And so that's the only use for the book at this point, is that they have examples ready to go. Anybody have a book so we can do one? No one? Okay. That's fine. I'll give you enough to do. All right, so let's run through the steps. And by the way, let me just say that for your own notes, you're supposed to do this. Okay. So this is solving a separable differential equation. By the way, there's a whole class called Differential Equations, which is a glorious class. And you'll be taking this soon, right? Very good. 1, get all of the variables on different sides of the equal sign. 2, then we'll integrate both sides. Both sides. And then 3, solve for y if possible. Okay. Now it gets a little bit ugly. Sometimes there's some differential equations that mimic reality, and when you solve them, you get down and you get an equation involving x and y, and you just can't solve for y, which is perfectly fine. You just leave it like that, okay?
But those are the steps.
And that is it. We'll end with that. All right, so let us get the test together, and then we'll end for the day. All right, so that on Thursday, we just get right to reviewing. Okay. I'll take any questions about what I'm asking for the test question, for the last test question. All right. So again, let me just say, for this question again, the only thing I'm asking is, can you read, disseminate, understand the story I'm going to tell? Right? That when I make it a turkey, are you going to freak out? Right? No, that's what I'm saying. No, I'm saying, and the way that you get ready for that is to do what? Practice. Right? If you do enough of them, it doesn't matter the story I tell, okay? But I'm going to put something in some other environment, and then it's going to get warmer or cooler. Indeed, if I had brought coffee in here, right, and then it would be getting cooler. But the problem doesn't change, okay? But instead, what changes? That minus sign becomes a, right, this minus sign becomes a plus sign, okay? All right. So 1, I'll ask you to define the integral from a to b of f of x dx and state the fundamental theorem of calculus. And these are all tentatives because, again, it just may be too much. My wife does this all the time. We'll go shopping. I'm sorry, she'll go shopping and I follow her. So I follow her around during shopping. And at the end, she says, well, I don't really want all of this. And then she starts to pick and choose, and she puts some stuff away. So that's what we're going to do here, right? Because some of this stuff may be too much to do. What's the second thing? Sir?
The second thing is not something that we've labeled. You said it was the way it's working.
Oh, no, we're not going to do those. We're not going to do those. Those are out. All right? Okay. Now, what's the new second thing? Say it again? Yeah. I think it is, yeah. All right, let's be real here. And again, I think there's just 2 of those. The 2. Okay. Hold me to this. It's on the record. Oh, no. There's no trig integrals. There's trig substitution.
There's no trig integrals?
No, because all the trig substitution at the end, trig and the trig integral. So I'm not going to ask you to do it twice. So trig substitution. So I did that in order to save us a little bit of time, so I could wreck you somewhere else. No, that's a joke. No, that's just absurd. So trig substitution. There's got to be 3 because there are 3 cases. There's x squared plus a squared, there's x squared minus a squared, and then there's a squared minus x squared. There are 3 cases there. I want you to be able to do all 3 of those cases. All right? And then that's where we littered the board.
How many cases were there?
3. So it's the square root of a squared plus x squared. There's the square root of x squared minus a squared, and there's the square root of x squared plus a squared. Yeah, those 3 cases.
Didn't you say that we have to do substitution and inverse substitution?
Yeah, that's what I meant. Yeah, that's what I meant. This is inverse trig substitution.
Okay, I was.
So there are no trig integrals, right?
Yeah, because you have to do the trig integral and the inverse.
Right. Right. Yes, no? Are we good? And then, what was after that? Partial fractions? Fractions, and then I envision 2 of those, okay? One in which you find what the constants A, B, and C are, or A, B, C, D, E, F, and G. You find those constants. And then the second one, you just write what the expansion should be, right? You don't have to find what the constants are. Please.
For number 3, the inverse trig, that's the a squared minus x squared.
Right, that's right. That's right. So we did some partial fractions. And then after partial fractions, I feel like it was, we've just done it.
Yeah.
Improper integrals? Yeah. This is a short one. I need to start adding some stuff. Oh, okay, right.
I want to have time to go back and.
No, we're not. We're not going to do improper integrals. Improper integrals. And again, you had just negotiated 2 of those. On an infinite interval and then on a finite interval. And then 6, we're talking about differential equations. We're talking about 16 points each. Okay. So differential equations, and then there are 3 of those, okay? And to be very clear, 1, you'll have to verify that something is a solution. Verify a solution. And that means that you need to show that P prime is equal to 3P, okay? Something like that. And then you need to solve 1. Solve a separable 1. And then there's going to be a word problem. And again, that's what I meant. It's just a turkey in the oven question. Okay? Simple. But as I said before, that the whole thing is just about integration. Okay? We'll start here on Thursday, and we'll just get right to it. Thank you.
Thank you. You are not picking